Good morning, chemists. Welcome back to this lecture, Chemistry 132B, Quantum Principles, Lecture 22. Time flies for sure. So we will be wrapping up the material for this course today and on Friday. So after Friday, there will be no new material introduced. So next week, we will be spending all of our time on practicing the material and doing some exam questions from previous years in the lecture. So we'll be going through some examples. I'll walk you through step by step, and there's also an opportunity just to have a discussion about the examples. For now, we'll be kind of concluding the molecular orbital theory part of this course. And on Monday, we started talking about the Huckel approximation for pi conjugated systems. So that was the topic on Monday. And we did that in a particular fashion. Namely, we diagonalized the Hamiltonian matrix. Okay, so matrix diagonalization is a very important tool in quantum mechanics. It can do things very similar to what we did with the variation principle. So these are two techniques that both give you, the energy of the new orbital states that you select. And the diagonalization method is in particular very attractive because it is a method that we can use for much larger structures than the structure you see here on the slide, which is the ethene molecule, which only has 2 carbon atoms that contribute to the pi conjugation or the pi bond. But we can expand this to include many more carbon atoms, and that's exactly the topic of today's lecture. You will see that this matrix diagonalization method is a very excellent tool to give us an impression of the energies of these pi bonds. And we can learn a lot about the stability and the properties of the molecules that have such pi conjugated bonds, including, of course, our favorite molecule, which is the benzene molecule, right? So some of this will sound familiar to you guys because I know parts of this have been covered in inorganic chemistry before, but here we'll try to do it in a very thorough way, hopefully. So from the bottom up, using this tool that we just discussed on Monday. Okay, so we'll start with this molecule, which is the ethene molecule, of course. Has 2 carbon atoms, has 1 pi bond, and each carbon atom contributes 1 electron to the pi bond. So there's 2 electrons in total that make up this pi bond. So what we're going to do is to find the energies of these pi orbitals. Okay, that's the goal. We're going to find energies. And the way we did that is by making a molecular orbital. Okay, so here we have psi b, which is a linear combination of the 2 atomic orbitals, right? So 1 and 2, the states 1 and 2 correspond to the individual p orbitals, the p orbitals that each of the carbon atoms has. Okay, so we're going to make a linear combination here. We can do it in 2 ways. Okay, because we can make a combination of plus and minus, remember? So there's 2 possible molecular orbitals that we can form. Okay, so we can call them psi b and psi a, and here they are. We don't know what the coefficients are, but those coefficients is what we will find through the process of matrix diagonalization. If we find a column vector matrix, then we know exactly what those coefficients will be for the bonding and the anti-bonding orbitals, along with their energies. So what we're going to do is we're going to write the Hamiltonian matrix and in terms of these molecular orbitals. Okay, so we know there's 2 molecular orbitals, we don't know the coefficients, and that is exactly what we're going to find by solving this problem through matrix diagonalization. So how do you do that? Well, this is the guiding principle, right? So you see the matrix, the Hamiltonian matrix, the bold H, and then we have to find these column vectors C. Okay, so once we have the column vector matrix C, then we have, of course, the diagonal matrix on the right, which tells us the energies. So let's make this explicit so you can see how this works. So I think last time we already concluded that the Hamiltonian matrix looks like the one written here. Okay, so this alpha is, of course, the matrix element. Let me just write it explicitly so we have no confusion about this. This is basically the Hamiltonian matrix element where I put psi A, okay? And the same here. This one is psi B and psi B. Okay, so that's alpha. And beta, of course, is also a matrix element where each matrix element is an integral, but now I have AB for beta here, and the beta below here is BA. Okay, so all of these alphas and betas, they are previously defined, but remember, these are matrix elements that are integrals, in fact, right? The integrals is what we find by looking at the examples here. We can diagonalize this. Actually, I should not do it this way. This is not really a good way. Let me just cross this out because they are actually defined in a slightly different way as before, where this is actually a, let me redo that. This should be 1H1 in terms of atomic states. This should be 2H2. Okay, apologies for that. This is not correct. This one is correct, right? So you basically have the matrix elements with respect to the atomic orbital states. So if I diagonalize this matrix of the alphas and betas, remember the alphas are on the diagonal, the betas are on the off diagonal. Okay, this is not a diagonal matrix, but I can diagonalize this matrix, and we have done that on Monday. We actually did that because we knew what the column vector matrices are, and then we diagonalized them. We found the following: alpha plus beta and alpha minus beta. Those are the diagonal elements. Now, those are the two energies that we find, and therefore we have alpha plus or minus beta as the result. Okay. So the big question is, can we do this in a more general way? Can we solve this problem in such a way that we don't have to know these the matrices C beforehand, because we knew what C was, because we solved the problem before with the variation principle. So this is kind of like, you know, prior knowledge. We had prior knowledge of the problem, which made it very easy to solve this diagonalization problem. But what if you don't have prior knowledge of what these column vector matrices are? Then you have a big issue. You cannot move on. Well, fortunately, it turns out that matrix diagonalization is a very general method that you can do numerically with very well-known solvers. Okay, so there's algorithms for that, and we'll use that actually on Friday. We'll see an actual implementation on how to do that. But the bottom line is that matrix diagonalization is a well-established technique where you start with a matrix, any matrix, and then your diagonalization solver can give you the result. And what it spits out are two things. It spits out the so-called eigenvalues on the diagonal, as well as the matrix that makes that possible, and that's the matrix C. So you get two answers, the matrix C and the matrix E, from this procedure. And that's exactly what we need. Okay, so what we find in this particular case, and this is exactly the same as on Monday, nothing has changed, is we have the atomic orbitals, one for the carbon on the left, one for the carbon on the right, and then we see the molecular orbitals in the middle, where we see that we have the energies alpha, which is the dotted line. That's the energy of the individual atomic orbitals. Okay, so that's alpha. That is this matrix element right here. Okay, so it's the energy of the Hamiltonian sandwiched between the states 1, 1, or between 2, 2. And since I have two carbon atoms they give the same energy. So they both have the energy alpha. The molecular orbitals are split up and down by a total of beta down or up, and that gives us my pi orbital. The bonding has an ungerade symmetry, and the anti-bonding has a gerade symmetry. So this is a common way to label these pi orbitals, pi u and pi g. Okay, so this is what this procedure tells you. Now, mind you, this is done in the Huckel approximation, and the Huckel approximation makes some pretty stiff approximations, okay? And that results, for instance, in now a purely symmetric molecular orbital diagram where the bonding orbital is split by beta down and the anti-bonding is split by beta up by exactly the same amount. You see that? So this is not an asymmetric molecular orbital, but a purely symmetric molecular orbital in terms of the energies of the bonding and anti-bonding orbital. Okay, this is slightly different from what we talked about before with the variation principle, where we found that the anti-bonding orbital was split more up than the bonding orbital was split down. Okay, and that is the result of the approximations that we have made in the Huckel approximation. Okay, they're pretty strict, and that leads to this simplification of the molecular orbital diagram. So clearly, this is very much an approximate picture, but still a very useful approximate picture, as you will see in the subsequent slides. So let's apply this principle to a more complicated molecule. Here is, we have now 4 carbon atoms in the chain. Okay, so this is having 2 pi bonds here, but these pi bonds are conjugated. This is butadiene. It's a conjugated system where each carbon atom now partakes in the pi bonding network. Okay, so this is a pure conjugation. Conjugation, of course, means that you have a pi bond, single bond, pi bond alternating, right? So that's the case here. That means that all these carbon atoms contribute to the pi bonding network in the same way. Right, so we have 4 atomic p orbitals that partake in the pi bonding formation, and that means that we now have 4 molecular orbitals, pi orbitals. So 4 atomic orbitals in, 4 pi orbitals out. 4 atomic orbitals in, 4 molecular orbitals out. Okay, so what do these molecular orbitals look like? Well, they are linear combinations, of course, of the states 1, 2, 3, 4, where 1, 2, 3, 4 are simply the pi, sorry, not the pi, but the p atomic orbitals of these individual carbon atoms. So let's say the first one is 1, second one 2, 3, and 4. Those are the atomic orbitals, p orbitals, from which we're going to form the molecular orbitals. This is only one combination. There are a total of 4. Okay, and of course that's determined by whatever these coefficients are. So our job is the same as before. We have to find those coefficients, right? So we have a total of 4 states. Each one has coefficients. They're all different, but they're all a linear combination of these 4 states. Our job is to find the coefficients for all these molecular orbital wave functions. You can call them psi A, B, C, and D. So we do it in exactly the same way. We're going to look at the Hamiltonian matrix, and we're going to try to diagonalize this matrix. All right, so what does the Hamiltonian matrix look like? Well, here it is. In the Huckel approximation, it is really simple, because all these alphas are, of course, the energies of the atomic p orbitals. Remember, this is, I'm going to write it one more time. Just make sure that it's clear, because I made a mistake on the previous slide. This is basically the energy of the p orbital of atom 1, right here, right? This is the one for atom 2, 3, and 4. So those are the alphas. The betas are now the integrals, where I have on one side a different orbital than on the other side of the integral, right? So the bra and the cat are different. So this beta here is looking at 1 and 2, the kind of overlap integral between these 2 guys with the Hamiltonian sandwiched in between. That's what this beta is. The beta on the other end looks very similar but the bra and the cat, the 1 and 2, have switched positions, right? This one is 0. Why is that? Because this one would be the overlap with the Hamiltonian in between, sandwiched between the first one and the third one. But we just concluded in the Huckel approximation that we only consider nearest neighbors. So we only consider 1 and 2, but not 1 and 3. Okay, so that's why there's a bunch of zeros that are farther away than 1 step from the atom. And that means these are not nearest neighbors. The only nearest neighbors are the ones on this line here that is adjacent to the diagonal. Okay, so that is the kind of composition of the Hamiltonian matrix. It has the alphas, it has the betas, but it has also zeros. Those are the zeros that we enforce through the Huckel approximation. Okay, so they are not 0 for real. They are 0 only because we say they are through the Huckel approximation. So this clearly is an approximation. So what do you do with this matrix? Well, the good news is, again, as you will see on Friday, you can write this matrix in such a way that you can put it into a numerical solver and then diagonalize this matrix. Okay, so you just need only one piece of information, that is this matrix. This matrix can be diagonalized just by the sheer fact that you know what its values are. And if you do that, then you can find the following. So after you put it in the solver, you get basically this answer. You get the matrix E, where you have the so-called eigenvalues, which are the energies, on the diagonal. All the other elements are now 0 because the matrix has been diagonalized, right? So what are these values that we find? Well, we find alpha plus, and then a number, 1.62 times beta, alpha plus a number which is looking very similar, but this is actually 0.62 beta, and then alpha minus 0.62 beta, and then the last one is alpha minus 1.62 beta. So I find 4 values of the energies. These are the energies of the molecular orbital states. So I found now my molecular orbital states and their energies. What do the orbitals look like? Well, that depends, of course, on the coefficients, which I also get from this diagonalization procedure. Again, we will show you on Friday exactly how that works. These values come from the diagonalization procedure. So I have diagonalized it numerically. Again, I will show you on Friday exactly how that works. And the result of this diagonalization is that we now have diagonal elements where these are the correct values. These are the eigenvalues of this problem. Okay, so we have solved this now numerically. Okay, so what we find are these energies, alpha plus minus 1.62 beta and alpha plus minus 0.62 beta. And that means now we can make kind of an orbital, molecular orbital diagram with these values. So let's have a look at that. The lowest energy is alpha plus 1.62 beta. Remember, both alpha and beta are negative values. So plus this value basically means you go down more, okay? So here's the butadiene molecule. This orbital, if we look at what it looks like, we can find the coefficients through this procedure. We find the coefficients. That means we know what the orbital is going to look like, and it looks like this. It looks like that all the orbitals, both below the plane and above the plane, have exactly the same phase, which means the same sign. And that means that it is a continuous orbital both below and above the plane. Okay, so this is the most bonding orbital that we find, and it has the energy, which is, of course, the lowest. The lowest energy is the most bonding orbital. Then the next one in line is alpha plus 0.62 beta, and it looks like this. Okay, it looks very similar, but now I have a nodal plane smack in the middle. All right, where basically the sign flips. So there's one nodal plane. I see 2 of these atoms are in phase above and below the plane, then a nodal plane through the middle of this molecule, where on the other end, the remaining 2 carbon atoms have a flipped phase relative to the first 2 atoms. Okay, so this, of course, has a higher energy. Why does this nodal plane introduce a higher energy? That is because every time you introduce a lot of curvature in the wave function, the kinetic energy must go up. All right, must go up. So because if I go from one carbon here to the next carbon over, I have to make a huge swing in the wave function to make that, to go through the nodal plane here. Okay, and that creates a lot of extra kinetic energy, and that leads to the higher value of this orbital relative to the one below it. Okay, so here's the third one in line. It has the energy alpha minus 6.2 beta, and it has one more nodal plane. So now I have a nodal plane here between the first and second carbon atom, and a nodal plane between number 3 and 4. Okay, so 2 nodal planes means even higher energy. And then the last one has a nodal plane through all of the bonds, all of the carbon-carbon bonds, all the pi bonds. So it's now an alternating phase between each of the p orbitals. Okay, so this is still a molecular orbital, even though it has nodal planes between all of these orbitals, right? Between also all of these atoms. This is evidently the highest energy situation, and it has the energy alpha minus 1.6 beta. Okay. So this is what we then find for the energies. You see a very nice arrangement: 2 energies that are lower than the alpha, 2 energies that are higher than the alpha. The anti-bonding, of course, are the ones with the higher energies, and then the lower 2 are the one with the bonding character. Note that even though you have one nodal plane, okay, one nodal plane is not enough to destroy all the bonding character. This is still considered a bonding orbital with an energy that is lower than alpha. Okay, so the first 2 are bonding orbitals. They give lower energies than the alpha energies, and the last 2 on the top are the anti-bonding orbitals, which have energies higher than the alpha energies. Again, I like to emphasize that because beta is a negative value, if there's a negative sign in front, it means in fact that you go up and not down. Okay, so keep that in mind. Okay, so here's the next molecule we will consider. It's very similar to the previous one, but this is cyclobutadiene. Okay, so very similar, but now it's a circle, cyclic structure. And the solution to this problem is also very similar to the previous one. We're going to set it up in exactly the same way. We have 4 atomic p orbitals. We are going to form 4 molecular orbitals, pi orbitals. Okay, so again, the same recipe. We have 1, 2, 3, 4. Those are the atomic orbitals. We have to find the coefficients. We find the coefficients through diagonalizing the Hamiltonian matrix. Remember, there's a total of 4 molecular orbitals. So we'll find a total of 4 orbitals after we solve this entire problem. The general recipe is the same as before, but now the matrix looks a little different from the one on the previous slide. Okay, and I think we know why. What is the difference? Well, we can see that there's now a beta here, but previously there was a 0. There was a 0 for the regular butadiene, but there is now a beta here at this position for the cyclobutadiene. And I think we all understand why that is. That is because this carbon atom 1 over here, let's call that number 1. Okay, 1, 2, 3, and 4. Okay, what are the nearest neighbors? Well, there's a nearest neighbor between 1 and 2, but not between 1 and 3. So that's going to be a 0. Okay, so that's the alpha. That is the nearest neighbor between atom 1 and its neighbor 2. Then the third one is going to be the neighboring 3, which is not really a nearest neighbor, and therefore the beta is going to be 0 according to the Huckel approximation. But atom number 4 is again a neighbor of carbon atom number 1, and therefore this guy here is not 0, but is actually beta. Okay, so if you have a cyclic structure, then the extremities on this diagonal here, the extremities are going to be not 0, but it's going to be having a value beta. For the solver, the numerical solver, the structure of this matrix doesn't really matter. You can throw any matrix into your numerical solver and it will spit out for you the values of the diagonal, okay? And if you do that, if I throw this matrix into my numerical solver, this is going to be the answer that comes out, okay? So what I find after I do this procedure, again, if you're confused by this, we will go through this procedure step by step on Friday, okay? So that is when I'm going to reveal how to do it, and you can do it yourself. In fact, it's going to be a homework exercise next week on doing exactly that, and you'll see it's really not that hard. So what we find after diagonalizing this matrix, we find, of course, that we have one, namely all the matrix elements are going to be 0 except the values on the diagonal, and therefore these values are going to be my energy values of the problem after I solve this problem. So I find the energies alpha plus 2 beta, then 2 energies of the value alpha, okay, and then alpha minus 2 beta. So these are values that are a little different from the values that I found for the linear butadiene. So the cyclobutadiene has a set of different values in energy for the molecular orbitals of this pi conjugated system. So here they are once again, alpha plus 2 beta, then alpha alpha, and alpha minus 2 beta. As you can see, I find 2 energies, this one and this one, that are actually the same as the energies of the atomic p orbitals. So they have exactly the same energy. So here I find 2 molecular orbitals whose energies are in fact the same as the energies of the p orbitals, okay, the atomic orbitals. So that means that these alpha alpha, they neither are bonding or anti-bonding. There's no gain or loss relative to what I had already for the atomic orbitals. So that's a special case. And they're called actually non-bonding molecular orbitals. Okay, so not anti-bonding, but non-bonding. They have no energy different from the original atomic orbitals. So this is what it looks like if I put the molecular orbital diagram together. I find the following. I find 4 solutions, and I can label them as pi 1, pi 2, pi 3, pi 4. So that is the only reason why I have 1, 2, 3, 4, simply because I start with number 1, 2, 3, 4. That's it. Okay, there's nothing else to it. So the lowest one is going to be the most bonding one. That's alpha plus 2 beta. And then I have 2 that have the same energy as the original atomic orbitals, namely the value alpha. And then 1 really anti-bonding orbital, that's alpha minus 2 beta. So what do these orbitals look like? Well, they look like so. This is basically the cyclobutadiene looked at from the top. Okay, so I'm looking at it directly from the top, top view, so not from the side. Okay, so I can see the actual square here of the how the carbon atoms are oriented. And the lowest orbital in energy is, of course, the most bonding orbital, where all the phases are going to be the same between the individual p orbitals from the carbons. So I indicated here with yellow. There's, of course, a blue color at the bottom, but since I'm providing not the side view, but the top view, you don't see the blue color at the bottom. Okay, but there will be, of course, because these are p orbitals. So this is a fully bonding one. There's no nodal planes in this molecule in the pi conjugated network. So what about pi 2 and pi 3? Well, they look like so. You can see now that you see some blue, and that's because there's a phase flip or a sign flip between these 2 adjacent molecules here. Same for here. These 2 molecules, in between, there is a phase flip. There's no phase flip between this molecule, sorry, this atom and this atom here. All right, so we have one nodal plane, and the nodal plane is right here. Okay, same for this pi 3, which looks exactly the same. The whole thing is simply rotated by 90 degrees. So I have, again, a nodal plane that goes right there, right? And then the last one is having one more nodal plane, and I'll draw them in a second so you can see them explicitly. But now I have an alternating sign between each of the adjacent carbon atoms. All right, so the molecular orbital now has between adjacent carbon atoms, molecular orbital changes sign. So let's draw those nodal planes explicitly. For pi2, it's right there. For pi3, it is the same, simply rotated by 90 degrees. So these orbitals, pi2 and pi3, are really similar, and therefore they have the same energy as well. And then the pi4 molecular orbital has two nodal planes, and they can be drawn in this kind of cross-like way. Okay, clearly it's evident that this orbital must have the highest energies because it has a lot of curvature. The molecular orbital has a lot of curvature to swing from one atom here to the next. You have to go from plus to minus. That means a lot of curvature, a lot of steepness of the amplitude of the molecular orbital, and that leads to a higher kinetic energy and therefore to a higher energy overall. Okay, so this is cyclobutadiene. Let's now go to benzene. We have to talk about benzene, of course, and we're going to do exactly the same procedure for benzene. Okay, so we're going to have 6 carbon atoms, 1, 2, 3, 4, 5, 6. And each one contributes 1 p electron to the pi conjugated network. All right, so and this is the matrix that I can come up with, where the alphas now are the energies of the individual atomic orbitals. Okay, the betas are the kind of cross integrals between nearest neighbors that are not 0 according to Huckel, but the next one over are going to be 0 because those are not nearest neighbors. Those atoms are not next to one another. That means that the integral that's made from them is not going to be having a finite value, but in fact it's going to be 0. The same for this row right here, also for this one. But then finally, this is going to be nearest neighbor again, because if I start at atom number 1 over here, okay, that's 1. This is atom number 6. They are nearest neighbors again. So this is basically this integral right here is 1h6. That integral, that beta integral, is not 0, and in fact is having a value beta. Same for this guy, okay, because that's going to be 6h1, right? So that's why they have the values that are finite and not 0. So again, I have my Hamiltonian matrix. That's all that I need. I'm going to diagonalize this matrix using a numerical solver, and then out what I'm getting are the diagonal energies. Those are the eigenvalues. And I'm also getting the matrix C, which is basically the column vector matrix. And that's what tells me the coefficients of the molecular orbitals. So I know what the molecular orbitals are going to look like. All right, so if you do that, then you find on the diagonals, we don't have to explicitly write out the matrix again. We just need to know what are the values on the diagonal after I diagonalize this matrix. And what you find in this case are 6 different values: alpha plus or minus 2 beta, alpha plus minus beta, or alpha plus minus beta. Okay, so in fact, you see there's some similarity between these two guys here. So let's put this into a molecular orbital diagram. So we just order these energies, and shown here on the left are the actual orbitals, molecular orbitals that we find. We find them through the coefficients. Okay, we know what the coefficients are, so we can just plot what these molecular orbitals look like, and this is what they're going to look like. The energies associated with them are pi1. I always start simply labeling my first one with 1. The lowest one is simply called 1. That one has an energy alpha plus 2 beta. The next 2 over, I call them 2 and 3. That's alpha plus beta. They have the same energy, so they are degenerate, these two guys. Then the next one over have anti-bonding character. You see this plus is now changing into a minus. That means you add beta to the energy here. Beta, again, is negative, so if you add it to the alpha, and that means that you are now having more energy than the original atomic orbital. So this is unfavorable. Pi 4 and 5 are the first anti-bonding orbitals, and then finally pi 6 has an energy of alpha minus 2 beta. The highest energy is the most anti-bonding orbital. So again, there's the same kind of trend here. The lowest orbital is the most bonding, of course, and has no nodes above and below the plane of the molecule, right? So you see that all these orbitals have the same phase. All these p orbitals of the atoms have the same phase, and therefore they form a continuous molecular orbital that stretches out over the entire molecule, right? The next one over has a one nodal plane, pi 2 and pi 3. They are very much equivalent because they have only one nodal plane and they have also the same energy. They are degenerate, in fact. Pi 4 and pi 5, they have two nodal planes. Okay, here they are. I can draw them, one in a cross-like form. This one is a kind of a compressed cross, if you want, more like an X-like shape. But the result is the same. There are two nodal planes for pi 4 and pi 5, and therefore they must have higher energy than the orbitals before them. And finally, three nodal planes for pi 6. Okay, so that must have the highest possible energy. A lot of curvature in this molecular orbital, and that means the higher the curvature, the more kinetic energy the electrons have in this orbital, and that means it pushes the energy up. This energy is very anti-bonding. You can already see that there's no likelihood of finding electrons anywhere in between these atoms, and that means that the atoms will experience a lot of pushback relative to one another, and this creates a very anti-bonding situation. Okay, so these were a bunch of molecules we discussed. The ethene molecule, the butadiene, cyclobutadiene, and then the benzene molecule. And we found energies for all of them. All right, and here are the molecular orbital diagrams of the molecular orbitals of the pi conjugated system for each of these molecules. So let's walk through them, and I'm going to show to you that, all these cases have slightly different stabilization energies based on the pi conjugated network in these molecules. So let's look at that for a second. What we have to do is we have to fill out the number of p electrons that are going to participate in the pi bonding network, right? So in the first case for ethene, of course, I have two p electrons. Each carbon atom contributes one electron that's going to partake in the pi bonding network. So I can fill out the first two in the pi 1 here. That's it. So there's nothing in the anti-bonding, because this is a purely bonding situation here, and that is very favorable. Okay, so I can calculate what the energy is of this pi conjugated system. I have 2 times alpha plus beta. Why 2? Because each electron sits in an orbital. The orbital is the bonding orbital, which has energy alpha plus beta, times 2 because I have 2 electrons. So what I find is I find 2 alpha plus 2 beta. So that is the energy that the molecule would have from just one pi bond. Okay, so one pi bond, the bonding character is 2 alpha plus 2 beta. Now, what if I have 4 carbon atoms participating in the pi conjugated network? Then I have, of course, 4 electrons filled out in this molecular orbital diagram. Okay, so 2 here in pi 1, 2 in pi 2. If I add up the energies, I find 2 times alpha plus 1.62 beta. These are the electrons in this state, okay, because this state has this energy. And I have 2 electrons, so that means 2 times this energy. Then those 2 electrons are these 2 times alpha plus 0.62 beta. That is the energy of pi 2. Okay, so let's do that. I just add this up, and what I find is 4 alpha plus 4.48 beta. Okay, so what is interesting about that? Well, if I compare that with what one pi bond has, this is one pi bond. One pi bond has 2 alpha plus 2 beta. So if I have 2 independent pi bonds, it's basically twice the energy here. So that would be 4 times alpha plus 4 times beta. That's not exactly what I find here. I find 4 times alpha plus 4.48 beta, not 4, but 4.48. So I have an extra energy of a total of 0.48 beta that I have because these two pi bonds are not independent. In fact, they are conjugated. So this is a so-called conjugation stabilization energy. There's an extra energy here in this butadiene molecule because of pi conjugation, okay? And you can compute it. According to this Huckel approximation, you can just fill out what this beta is. You can compute beta numerically and multiply by 0.48, and you find negative 115 kilojoules per mole. This is a significant energy, stabilization energy that you find because of pi conjugation. I think everybody knows that pi conjugation helps the molecule become more stable, but here we can actually compute it and see why that is. So let's do the same thing for cyclobutadiene. See what we find there. Again, 4 electrons. Okay, so I'll fill them out. But now I have 2 here, and then 1 in pi 2 and 1 in pi 3, like so. Right? Now remember, pi 2 and pi 3 are just having the value alpha, so they don't really enjoy any stabilization. So what I do is I just calculate this for these 2 electrons, and if I add up the total, I find the total energy of these pi electrons are 4 alpha plus 4 beta. Now that is exactly twice the amount of ethene. Okay, so in effect, I'm just having 2 independent pi bonds. I don't really benefit from any conjugation. Okay, so even though I have a linear butadiene that has a stabilization energy, there is no stabilization energy in this cyclobutadiene. According to this calculation, this is exactly true. So even though it looks like it's fully conjugated, this conjugation here in this 4 ring doesn't lead to any extra energy stabilization through the pi conjugation. Okay. What about benzene? We know benzene is very stable. Let's prove it. Okay, so we have 6 p electrons, 2 go into pi 1, 2 in pi 2, and 2 in pi 3. And then we add up the energies of all these electrons. If we do that, we find that the energies in the pi conjugated network have a total energy of 6 alpha plus 2 beta. If I just look at it at this picture, it looks like I have 3 pi bonds. 3 pi bonds would give me 3 times this value here of ethene. That will be 3 times 2 alpha plus 3 times 2 beta. That will be 6 alpha plus 6 beta. But I find 8 beta, so I have 2 beta stabilization energy. Okay, so benzene has a stabilization energy of 2 beta, which is minus 460 kilojoules per mole. It's enormous stabilization energy in benzene due to this pi conjugated network. All right, so that is significantly more than we saw in butadiene, and clearly a lot more than in cyclobutadiene, because this molecule really doesn't enjoy this stabilization. So there's a so-called Huckel rule that says, okay, if you have a structure like this, like benzene, you benefit from aromatic stabilization. That is a situation where this conjugation is particularly strong, and that holds for cyclic molecules. Okay, what you need is a condition that fulfills this little equation here below, 4n plus 2, where n is an integer that starts at 0 and then is 1, 2, 3, 4, 5, and so forth. So if I put in the lowest number, which is 0, the lowest number of p electrons that I can have is 2 to enjoy the aromatic stabilization. Okay, now we'll see an example of that next time, not now. But the next one over is when n equals 1. 4 times 1 plus 2 is 6. That is benzene. Benzene has 6 p electrons that participate, and therefore benzene is classified as a molecule that's aromatic and therefore enjoys aromatic stabilization. All right, so we'll see more examples of that. We'll see some example where n is actually 0, and we'll see how that works out. Turns out you need a ring of at least 3 participating carbon atoms, and we'll talk about that probably on Friday. Okay, so here we see the lowest or the highest occupied molecular orbital. That is the pi 2 and 3, and then the lowest unoccupied molecular orbital, pi4 and pi5. And of course, if I will be exciting my benzene molecule, then the transition that will happen would be the transition of one of these electrons to the LUMO, one of the HOMO electrons to the LUMO states, right? That will be a transition of benzene. A lot of aromatic compounds and conjugated pi systems, if you excite them in the visible range of the spectrum, then we have the so-called pi to pi star transition. Those are these transitions. That is the transition that happens, and that is what gives the molecules color. In benzene, that color is going to be too far to the UV, so benzene looks very transparent to the eye. But for a lot of other pi conjugated systems like dye molecules, this pi to pi star transition actually is invisible, and it gives the molecules color. That's the reason why a lot of molecules have these beautiful colors in the visible range. Okay, so just a kind of a few notes. Okay, we saw that we solved this molecule. We solved this Hamiltonian matrix. We diagonalized it for benzene, and we found some values. And those values are very instructive. But we have to realize, of course, that this is happening under the Huckel approximation, which is quite severe approximation. Okay, in particular, we basically say that all these beta integrals are going to be 0 if n and m, these are the two atoms, are farther away than one step. They're not really adjacent to one another. And that is really a pretty dramatic approximation. Okay, so here we have the full Hamiltonian. We talked about this before, but you see it has several terms in there. It basically sums over all electrons here. Okay, so I'm summing over all electrons. All the distances between all the different electrons is basically taken into consideration. Here too, I have like all the electrons that interact with all the other atoms. That is all crossed out in the Huckel approximation. Okay, so it's pretty stringent, and these contributions do have an effect. Of course, we cannot simply say that they don't matter. They do matter. And at some point, they're going to change the result quite a bit. All right? So this is a general challenge. In fact, in computational chemistry, there's a nice quote by Paul Dirac a long time ago, 1929. And he basically says that, look, we know everything. We know the fundamental laws. Okay? It's not the laws that are the problem. We can exactly write out this Hamiltonian and exactly write out what you should compute to find the answer. The problem is not the description. The problem is really how to actually solve the resulting equations. Okay, so the equations that we have are too complex to be solved. Okay, so we need basically approximate and numerical solvers to find the answers in cases like this. Well, the good news is that we have, of course, such packages, software packages. Maybe you've worked before with Gaussian. Gaussian is pretty user-friendly software package, and we can compute the energies of complicated molecules, the lowest possible energy, the ground state energies of fairly complex molecules. It's very powerful. And some of the ways in which Gaussian works, there's much more to it, but some of it is actually based on the mechanisms that we talked about in this class. So matrix diagonalization is an important part of the Gaussian program. You can do some amazing things. Okay, so here's I think this is a beautiful picture of a very complex structure where we compute the pi conjugated network using one of those software packages, and you find, really what the electron density is in the pi conjugated network throughout the entire molecule. This gives us a very close-up view of, the properties of this molecule, which is of course governed by where these electrons are, right? Yeah, so fullerene, absolutely, that's correct. So in general, what we do with those programs is, of course, compute the energies of, let's say, the highest occupied molecular orbital and the lowest unoccupied molecular orbital, and we can see really what is the electron density in these complex molecules, and understand what happens if you excite from the ground state to an excited state, right? You can see that the orbitals that partake and these structures are very complex. You could never do this by pen and pencil, so you definitely need computers for this purpose. But the beauty is that the principles are still very much the same along the lines of what we talked about. Right? So when you use these programs, it's really good to keep that in mind. You know, what these programs are really based on is directly related to what we have talked about. Right? Now, with these programs, of course, we can get a great amount of detail and insight in the properties of these molecules, why the molecule would have a certain color, for instance, and why it has a certain stability, or even its reactivity. It all depends on where the electrons are in the ground state or in the excited state. That explains very much the properties and molecular behavior of these structures. So pretty powerful stuff, okay? All based on quantum mechanics, of course. And hopefully, you know, this discussion here makes you appreciate a little bit, you know, the power of these methods. Okay, I'll stop right there. 1 minute over time, so it's a good time to stop. If there's any questions, let me know. All right. Any questions about this particular topic we just laid out?
I had a really quick question.
Yeah.
For your 4-carbon cyclic structure,
yeah.
When you were solving for their energies, how did you determine that it was non-bonding for the alpha and alpha energy?
So that's a good question. So we have 3 terms, right? One is the bonding, one is the anti-bonding, and then we have non-bonding. What does non-bonding mean? Non-bonding means that there is no energy stabilization nor destabilization happening. So basically, the energies of the molecular orbitals are identical to the energies of the atomic orbitals, in this case, alpha. So if I find a molecular orbital with an energy alpha, then I label that molecular orbital to be non-bonding because it doesn't provide anything beyond the energies provided by the individual atomic orbitals. The anti-bonding, of course, creates a situation that is less desirable, and the bonding a situation that's more desirable. The non-bonding doesn't do anything. That's why we have that terminology.
Okay, thank you.
Yeah. All right. Thank you, guys. Hopefully see you on Friday. We'll be doing some nice computations with the matrix solver. So we're going to do some live diagonalization. Stay tuned.